Hello everyone. This particular lecture in this series will see Lyapunov theory, and it will be followed by extensions of the theory within the same concepts in the next lecture as well. Actually, these are heavily used in nonlinear system analysis as well as system design, that means control system design also. We will see some of those applications as we go along, but let us first understand the theory part of it. So, outline of this particular lecture will be something like first is motivation, then followed up with followed by some sort of definitions, some little bit conceptual things. Then we will go to stability theorems, and most of the theorems we will not worry about proofs part in this lecture. We will continue with the conceptuals, concepts only. And then I will continue with this applications of this theory, this Lyapunov concepts for linear time invariant system stability. There are reasons for doing that also, and then we will see one or two theorems for instability, that if you are not successful in applying for like stability analysis, then obviously there may be some chance that the system is unstable. So, we need to have some conceptual things for instability analysis as well. Then towards the end of this lecture, we will also see some sort of construction of Lyapunov functions, because some ideas are there that how do you construct Lyapunov functions and all. On the way we will see a lot of examples as well actually. References, I have largely taken this material from first two, but all the three books are very good books, and there are some revised editions available as well for Khalil. So, maybe you can think of buying some of that if you are interested actually. So, when you talk about nonlinear systems analysis and design, there are variety of ways that you can do that. There are a lot of techniques. First is phase plane analysis. This is valid for small systems like second order system and things like that. Can be extended or mostly up to third order, but beyond that graphical interpretation is difficult, and hence we do not use that. And then there is differential geometry based concepts. Some of that we have seen that already, that is feedback linearization based or dynamic inversion concept. Then Lyapunov theory, that is what we are going to see in this class and next class. But other than that, there are techniques like neural network, fuzzy logic, genetic algorithm, all these fall under the intelligent control technique. And then there are concepts like describing function analysis, and there are optimization theories like optimal control theory based and all that actually. So, there are variety of techniques that are available to us to deal with nonlinear systems. Okay, so techniques are also getting developed, but the conceptual things are already available actually. So, anyway, we will talk about Lyapunov theory here. So, motivation for Lyapunov theory is something like this. First of all, the eigenvalue analysis concept does not hold good for nonlinear systems. Okay, because eigenvalue concept is related to matrix, and matrices means you should describe the system in the form of a kind of a x dot equal to x plus b, where the matrices come in actually. If you do not have matrices, you cannot talk about eigenvalue concept at all actually. Still, these eigenvalue concepts are useful in an indirect way sort of thing in this nonlinear system as well, but in general they are not available, and hence we will not worry so much on that actually. Second thing, nonlinear systems can have multiple equilibrium points as well as limit cycles. These are typically not concerns in linear systems actually. And stability behavior of nonlinear systems need not always be global. Okay, so, when you discuss about linear systems, they are typically global. When the linear systems do not worry, the stability behavior of linear systems are initial condition independent actually. That means is global theorems and all that. But here we will be seeing that most of the time we will be able to conclude only local stability. Global stability is difficult to kind of infer actually. And need of a systematic approach that can be exploited for control design as well. That is what we are mostly worried about. We not only want to have understanding or analysis technique, but we are also interested in exploiting the same to design control systems actually for practical usage. So, that is another motivation. So, all this motivation intact, we will study about some definition concepts and all that, and then see how we exploit this. So, when you are in this particular lecture, when you discuss stability definitions and all that, we are mostly worried about homogeneous systems. X dot equal to f of x, there is no u component part of it. But if u is designed as a feedback system like state feedback form, then this also kind of includes that. Okay. If you put u equal to phi of x, then f of x u is nothing but f of x ultimately basically. So, that way it is x dot equal to f of x. So, we talk about some sort of homogeneous system dynamics, and that is what Lyapunov theory is all about actually. So, the conceptually Lyapunov theory can be, I mean there are extensions of this to talk about non-autonomous systems as well. That means f of x is not only a function of x, but explicitly function of time as well. But here we are not talking about that also, we are simply talking about x dot is f of x. Okay. So, that means it is autonomous as well as homogeneous system. Okay. And this f that we are discussing, this function f is defined in a subset of Rn, which is D, and it takes the domain D, the function is defined, and its range is in Rn actually. So, it can start from D and then the mapping can be in the entire Rn space, where D is supposed to be in a kind of open set as well as connected set. We will see that this what we mean by open set and connected set in the next slide. But before that, what you are interested is in this Lyapunov theory is that this particular system x dot is f of x contains some sort of equilibrium points actually. So, equilibrium points can be easily seen by enforcing x dot is 0 basically, right. So, when you do that, you enforce this x dot equal to 0, okay, then whatever solutions you will get for that particular thing, that will give you that equilibrium point, and that is what you are doing here. So, x c dot is f of x c equal to 0. So, solution of that will give you x c, and remember this x c solution need not be unique. Now, this is a nonlinear function, and then this equation solution may have multiple solutions actually. Yeah. So, you will be left out with a number of choices for x c, and for about each of these equilibrium point we are interested in analyzing the stability behavior actually. Okay. So, before we move on, what is open and connected set? These are the definition. When you talk about open set, a set A, which is a subset of Rn, is open if for every p that belongs to A, there exists a ball of radius r centered at P, which is also a subset of A. Okay. That means, I mean in a simplistic language, the boundaries are not included actually. Okay. As long as you do not include the boundaries, then there will always be some sort of neighborhood both sides, which will belong to that set actually. Okay. So, that is what it means open set. When a set is closed, that means you also include the boundary points or boundary lines and things like that actually. Okay. So, that is what we mean by open set. And what is connected set? Connected set is a set which cannot be represented as the union of two or more disjoint non-empty open subsets actually. Okay. That means, if you construct any set A, you cannot represent by union of a number of disjoint subsets actually. Okay. And intuitively it is a set with only one piece actually, and that is what the picture tells you. So, for example, set A, what you see here, okay, is like a connected set, and set B, what you see here, I mean this bottom side what you see here is certainly a kind of a non-connected set actually. Okay. If you concentrate on A is a connected set, B is a non-connected set sort of thing actually. So, why does that happen? Because if I start with any point in A somewhere here wherever actually, then any point in A, any 2 points I can always join them, okay, without leaving the set actually. I can connect these 2 points without leaving the set, and that is the meaning of a connected set. And we are interested in that because the trajectory of the system that we are talking about has to evolve within the set itself, right. If it goes out of the set, then obviously you are not interested in that kind of kind of concept actually. So, what you are demanding here is D has to be an open set as well as a connected set actually, and it will admit some equilibrium points, and about each of those equilibrium points we want to know whether the system is stable, unstable, or I mean is locally stable or globally stable, or there are various concepts actually. And when you talk about nonlinear systems, so the definitions have to be carefully remembered actually. So, that is what it take us to little more definition concepts. Okay. First is what you mean by stable equilibrium. Okay. And by stability we do not mean that it unlike linear systems, we do not mean universal stability. I mean it is not just a unique definition actually. There are various definitions, and first definition what you see here is what is the weakest notion actually. Okay. That means Xc, the equilibrium point Xc is stable provided for each epsilon greater than 0 there exists a delta which can be a function of epsilon which is also greater than 0, such that if I start within this delta bound, okay, initial x of 0 is initial condition is close to the Xc equilibrium point within a delta bound ball, then for any time greater than equal to t0, okay, initial time, I will never leave this epsilon ball actually. Okay. So, that is the concept. Okay. So, that means suppose any point there is Xc here. Okay, I start with some sort of a ball of let us say delta, okay, and then if my initial condition is somewhere, then I will evolve somewhere. So, that ultimately this there is some epsilon ball somewhere, okay, this is the okay. Okay, I start with that, okay, that is my x 0. Okay. If I start with a ball of radius delta, I will keep on moving around that, but I will never kind of I can go wherever I want, but I will never leave this space actually. Okay. So, that is and this epsilon what you are seeing here, okay, has to be finite of course actually. Okay. And this what it turns out is that this delta that you are talking about can be a function of epsilon actually, it need not be an independent thing. Okay. So, if it is independent, that is again a stronger notion and all that, but if I talk about a larger ball, okay, then I can start with a kind of a larger delta or smaller delta. I mean it is just what you are telling is a function of epsilon basically. Okay. So, it need not be an independently given bound actually. Okay. Whatever epsilon bound we are talking about, okay, delta can be, this is epsilon bound, delta can be a function of epsilon, and it may so happen that you can also talk about delta being larger and epsilon being smaller. Okay, that is also possible. Okay. So, it does not tell you that epsilon has to be smaller than delta or delta has to be smaller than epsilon, nothing like that. So, even if you start with a smaller bound and eventually stay in a larger bound, then also the system is called, I mean the equilibrium point is stable. However, as it is very clear that it is weakest notion of stability, we need more than that to understand, I mean to infer good behavior of the system actually. I mean after all the stability notion is nothing but defining what is a good or bad system actually really. Okay. So, obviously, if this weakest notion of stability is also not satisfied, okay, then only we call that the system is unstable actually. Okay. So, I mean that is the kind of contradictory note, I mean kind of definition. If the system is stable, it has to be stable at least in the weakest notion, okay, otherwise there is no meaning for that. Then we also need some sort of a convergent condition. I mean this definition is what is called as convergent equilibrium, that is nothing to do with stability. Okay. And see, remember stability is for all time t greater than t0, it has to remain within that epsilon ball actually, but convergent notion tells you that it in between it can go anywhere it wants, but ultimately when t goes to infinity my trajectory will converge to equilibrium point. Again if you see that conceptually, okay. So, conceptually like if I have got equilibrium point something like Xc here, I have some initial condition x 0, then in between I can go large deviation, but ultimately I will converge there. So, that can be epsilon bound can be breached actually in between. That means, if I go here and ultimately I come back and converge at Xc, then Xc is actually convergent equilibrium condition. Okay. So, that is that is the notion of convergent equilibrium actually. So, obviously, we need stronger notions of stability. So, how about combining both the definitions? Okay. So, okay, if you combine both the definition, that leads to something called asymptotically stable equilibrium point. That means, when equilibrium point is asymptotically stable, provided it is both stable as well as convergent. That means, it will never leave that epsilon bound, or ultimately it will converge to the the equilibrium point. So, if both the things happen, then only you call that as asymptotic stable behavior. Then there is a stronger notion that is called exponentially stable. So, here we are worried about not only it will go to 0, but it will go to 0 in an exponential decay rate, basically exponential rate of decay basically. What does that mean? That means there will exist some alpha lambda greater than 0 such that this particular relationship will always be satisfied. Okay. And remember, this one is the deviation of your initial condition from the equilibrium point. This okay, all these norms I mean whatever you see double bars and all, these are norms actually. Norms are nothing but distances also actually. Okay. So, if I start this initial condition, I mean this whatever x of 0 minus x of e norm actually gives us some sort of a distance measure of the initial point from the equilibrium point actually. So, this at any point of time x of t, okay, this is my distance from the equilibrium point, and at initial time t 0, that is my distance from the equilibrium point, and these two are related by this relationship where alpha and lambda are positive constants actually. Okay. That means, whenever I start with I mean this delta ball, okay, that has to be actually within delta ball of course for local stability behavior and all. If I start with this delta ball, then this relationship will always be satisfied. In the rate of shrinking is actually exponential, because this factor is there actually e to the power minus lambda t. Okay. So, that the rate of shrinking is exponential decay. Okay. And for further, okay, these are the definition. First, the three things we are worried about. First is what is stable equilibrium point, okay, and if it does not satisfy that, that is unstable. But if it satisfies that, then we will worried about I mean we are worried about convergent equilibrium condition. And if these two are both there, that means I mean equilibrium point is both stable as well as convergent, then we call asymptotic stable. I mean the equilibrium point is asymptotic stable, and then even stronger notation is exponential stable. So, obviously, the nicest thing to have in any problem is obviously exponentially stable, but also remember the more and more you demand or more and more powerful things that you want to show, it will also demand more and more difficulty actually. That means, you may or may not be able to show that in general. So, most of the time we are I am very happy to show asymptotic stability condition. If a equilibrium point is asymptotically stable, that is most of the time it is satisfactory actually. Okay. And also remember that this exponential stability behavior is invariably satisfied in linear systems. The linear system solution is given e to the power at anyway already basically. I mean it is dictated by that kind of a formula basically. And if linear system is stable, it is globally asymptotically stable, globally exponentially stable, but nonlinear systems you cannot talk about that. You have to be very careful about each of the equilibrium point, what kind of stability behavior that you are having actually. Okay. Now, for further discussions we will without loss of generality we will discuss that I mean we will take it that x is equal to 0, and if x is not equal to 0, then you do this coordinate transfer. That means, you define some sort of a new variable, okay, like something like z equal to x minus x e, and then convert z dot is nothing but x dot minus x e dot sort of thing, and if it is equilibrium then that is 0. Okay. And then you left out with x dot is f of x u or sorry f of x, and then this is f of x is nothing but z plus x e actually, and x e is a constant number. So, if you see this equation z dot is again f z actually. So, with that change of notation basically you will be able to proceed further. So, we are not, and as far as x e is concerned, it will consider as something like a constant number here. So, with this change of coordinate we will be able to proceed further. So, further discussion will invariably assume that x e is 0. Okay. Now, we need further definitions and all to discuss any concepts here, and these are concepts of positive definite, semi definite, negative definite, like that these functions actually. Okay. Now, a function v which is defined from domain D to R, the same domain D, but the output is a scalar variable, I mean scalar value. Okay. That is the difference here. So, we define a function v from D to R, it is said to be positive semi definite if it satisfies these two conditions actually. That means, this 0 belongs to D. Remember, 0 is an equilibrium condition now. So, when you talk about 0, not just origin, but it is the equilibrium point after change of coordinate actually. So, equilibrium point belongs to D, that is where the connected set comes into picture. We want to start from that set, so that equilibrium point is contained within that set basically, then only you can move around and probably go there actually. Okay. So, 0 is part of D and V of 0 is 0, that is that is a requirement actually, and for any other point, okay, that means V of x has to be greater than equal to 0. Okay. V of 0 is 0 anyway, but any other point x belongs to D, this V of x has to be greater than equal to 0, that is called positive semi definite. And if it is so that V of x is greater than strictly greater than 0 in D minus 0, that means just take out the equilibrium condition point and then for every other point V of x is strictly positive, then it is positive definite function. Okay. And similarly, you can define negative definite or semi definite with respect to the same definition if minus V x satisfies these conditions actually, or alternatively you can change the sign, greater than equal to becomes less than equal to, and this greater than strictly greater than becomes strictly less than actually. So, we know what is positive semi definite function, positive definite function, a negative semi definite function, and negative definite function actually, and these are all required as part of Lyapunov theorems. Now, here we are ready now we are ready to talk about the stability theorems and their meaning actually. Okay. So, what you are talking the theorem 1 and all these theorems what you are going to discuss in Lyapunov theory, these are, remember, these are all sufficiency conditions, they are not necessary at all actually. Okay, that means if these conditions are satisfied, you are guaranteed to get the stability behavior, but if these conditions are not satisfied with respect to that V of x that you have selected, then there is no guarantee. In other words, you cannot infer that the system is unstable. You may have to try out, with a different Vx or keep on trying out, or you have to ultimately show that the system is unstable using instability theorems and all that. But all these theorems, whether it is stability theorem or instability theorem, these are all sufficiency conditions. Alright, the theorem reads like this: let x equal to 0 be an equilibrium point of this system, okay, the regular thing that we started with, f is defined from D to Rn, and let V, this D to R, be a continuously differentiable function, okay, such that these conditions hold good. That means, V of 0 has to be 0, you have to select a V of x which satisfies this. V of x is greater than 0, strictly greater than 0 in D minus 0. That means, conditions 1 and 2 taken together, all that you are telling is V of x has to be strictly a positive definite function. You start with a positive definite function defined in this domain D, okay, same domain D. Okay, so, V of x is a scalar function defined in the same domain D, okay, and positive definite function, and with respect to that selection, the third condition has to be satisfied. In other words, V dot of x has to be less than equal to 0 in D minus 0, the same domain what you are talking about. V of x is positive definite, whereas V dot of x has to be negative semi definite, then x of 0 is stable actually. Now, there are a couple of comments due here. First of all, this V dot of x, how do you compute V dot? So, if you talk about V dot, okay, if you talk about V dot here, V dot is nothing but, so remember V is a function of x only. So, we will compute del V by del x, this is a vector now, because V is scalar, x is vectors, then transpose times x dot, that is by chain rule actually, and this is nothing but del V by del x transpose times x dot is nothing but f of x. So, we will end up with again a function which is like purely a function of x. So, that function we have to analyze actually. Okay. So, and remember this V of x is something that we choose. So, that means this satisfying these first two conditions are typically not that difficult, but V dot of x is related to, it is something to do with our selection coupled with the system dynamic equation that we have, f of x comes into picture actually. So, V dot what you want to analyze later is a function of both our selection as well as what system dynamics we have, okay. That is where the difficulty comes actually, because our selection and system dynamics may not match exactly actually. That is the first comment. Okay. The second comment, okay. The second comment is, if nothing is given, then V of x is something like, we typically like to start with something like x transpose x, let us say, that is certainly a positive definite function, okay, because if you take x equal to 0, it is 0, any other x, it is a positive right. It is strictly positive for all x not equal to 0 basically. So, if nothing is given to us, then this is certainly what we call as Lyapunov function candidate. That means, any selection that is positive definite is certainly a Lyapunov function candidate, but once the third condition is also satisfied, then we call that as Lyapunov function actually. That means, it has some meaning to the system dynamics that we call, that we have actually. Okay. So, if nothing is given, that is a choice. If this selection fails, then the other selection is like kinetic energy plus potential energy. So, we have, if you have a mechanical system or electrical circuit something like that, then if you take total energy of the system is kinetic plus potential energy, which is certainly guaranteed to be a positive quantity basically. So, with respect to that expression, you analyze V dot and things like that, proceed from there actually. But again, you may or may not succeed, and you may be able to give only limited inferences and all that actually. So, all those things may not be good for you. In other words, it may not be sufficient for inferring these stronger conditions and all that. We will see some couple of examples later actually. Anyway, the summary of the story is you select a positive definite function, and so that V dot is negative definite, okay, sorry, negative semi definite in the same domain. Then you can only infer that x equal to 0, that equilibrium that you are talking is stable. Okay. So, and remember, this is the weakest notion of stability that we just discussed. Okay. If you can only show this one, then you are just talking the system is stable. Okay. That means, you are getting some sort of a bounded solution, that is all you are talking, nothing more than that actually. Now, what about little more than that? We are mostly interested in this asymptotic stability anyway, then that is actually theorem 2, and carefully observe theorem 2, that is, this gives you asymptotically stable, that is the condition. Everything else remains intact, but the condition that changes here is only this one. This negative, less than equal to 0 becomes strictly less than 0. Okay. That means, V dot has to be negative definite this time. And if you, intuitively it feels, okay, what is the big deal actually, if it is negative semi definite, I can show that. But it turns out it is order of magnitude difficult actually to see any problem. If you really want to show V dot is strictly negative definite, it is an order of magnitude complexity actually higher. And many times you will be able to show that, but from here to there it will demand lot of work, we may not be able to show that also, and that is why we have to take help of some other theorem actually, which is Lassalle's invariance principle and all. We will also talk about that actually. Okay. But anyway, let us understand this is the basic Lyapunov theorems first. First thing tells you is start with a positive definite function, so that V dot is negative semi definite, so that equilibrium is stable. The next one tells you that V dot is negative definite, so that you can conclude asymptotically the equilibrium point is asymptotically stable. Then there is a third definition, these are all what we saw is local, okay, that means around a neighborhood only my solution will converge and things like that. What about global stability? And global stability is is valid provided there is one additional condition which tells you that V of x is not only positive definite, but V of x also needs to be radially unbounded actually. I have to select a V of x in such a way that V of x needs to be radially unbounded. That means, if the more and more I go away from equilibrium point, my V of x is going to increase more and more, it is never going to be decreasing and all that. What is an example? It is a very easy, that x transpose x that we talked about in 2 dimensional space, you can see that the function takes a shape of this something like this. Okay. This is x1, this is x2 let us say, and this is V of x. If you go more and more away in any direction from 0, okay, then obviously the function keeps on increasing actually. So, that those are functions called radially unbounded actually. Otherwise, this is a necessity condition, otherwise you will not be able to show the global behavior of the equilibrium, the stability condition basically. Okay. So, in other words, this additional definition kind of truncates our freedom actually. Okay, that we cannot take anything that we want, we have to select something which also has this radially unbounded property basically. And there are necessary, if you really want to think a little, that is something comes from level set definition. I am not going to discuss so much on that, but level set is something that that is a set for which the v of x has one particular value basically. Okay. So, let us say v of x is C1, that defines a set, v of x is C2, that defines a set, and you all the time you are interested in some behavior for which this my v dot negative definite does not necessarily mean that my level sets will keep on decreasing in a way actually. So, these are all different concepts, we will not worry so much in this particular course actually. Okay. But if you are interested, you can see some of those books have some nice examples which will clarify your concept why this radially unboundedness is necessary actually. There are counter examples also. If the radially unboundedness is not there, then v of x can keep on decreasing and it will never converge to origin actually, that is also there actually. Okay. So, that is a necessary condition, necessity here actually. So, if your v of x is positive definite, in addition v of x is radially unbounded and v dot is negative definite, then x of 0 is globally asymptotically stable actually. Okay. What about another condition? What about exponential stability? This theorem tells us that suppose all conditions of asymptotic stability are satisfied. Okay. In addition to that, there exists constants k1, k2, k3 and p such that this v of x is bounded both sides and v dot of x is also bounded from above actually. Okay. That what does that mean actually? Like v of x, see this asymptotic, these asymptotically stable conditions are already there with us actually. We want to see whether the exponential decay is there or not. Okay. In that, if you want to conclude, then this is the condition that you have to, that restricts our selection further, that v of x has to be bounded between these values. Okay. And v dot of x should always be less than equal to this minus k3 times x of p actually. And if you really want to see where is the application and can I show that example and things like that, you can do that for LTI systems. Okay. LTI systems, if you that linear time invariant systems, if you take x dot equal to a times x and you know that these eigenvalues of a's are actually stable. So, if I take lambda a and then sigma part of a is less than this is the condition necessary actually. Okay. This means the real part of the eigenvalues are all less than 0. We know for sure that the system is stable, and in those conditions you can actually show these theorems getting satisfied using the Rayleigh inequality actually. That means, if I talk about let me you have to excite a condition that it tells you that this x transpose A x, okay, norm of that in second norm especially is bounded both above and below using lambda minimum of A, then norm of x square, okay, and with lambda max of A into norm x square. So, if you use this theorem, you will be able to show that these conditions are satisfied for linear time invariant systems. All right, we will not digress this too much, we will keep getting focused here, and these are the necessary conditions for exponential stability actually. And obviously, if these conditions hold globally, that means D is Rn actually really, then origin is globally exponentially stable actually. And obviously, these conditions are more and more difficult to show, but for linear time invariant systems they are satisfied anyway actually. Okay. But other conditions also, suppose you are lucky in a particular nonlinear system, then probably you can if you are able to show this, nothing like that actually that way. All right, now time for some example to understand this thing better, and let us say start with this example with this pendulum without friction. So, let us say there is a regular pendulum, not inverted pendulum, and it actually oscillates about its vertical equilibrium point where the bob is down actually. Then what do you, if you define this x1 as theta and this x2 is theta dot, then this x1 dot and x2 dot, that is theta dot and theta double dot, if you start with that and all that, you will end up with this kind of equation in state space. And it is easy to derive that also, it is only oscillates under the influence of only gravity actually, there is no friction, remember that. So, obviously, intuition tells us that because there is no friction, it will keep on oscillating actually. So, obviously, we will be able to show only stability, not asymptotically stable behavior, because there is no energy dissipation actually. So, nothing will go down, so it will keep on oscillating. So, can we show that? Let us start with this Lyapunov function candidate. Very naturally we will take kinetic energy plus potential energy and we expand this term and tell okay, this is my expression to start with. Certainly it will satisfy the property that if x equal to 0, that means x 1 and x 2 are 0, then this term is 0, 1 minus 1 is 0 and this is also 0. So, V of 0 is 0. Any other point, any other condition, I have got some kinetic energy plus potential energy anyway. So, total energy is never going to be, total energy is always going to be positive actually. So, that I got a right candidate for Lyapunov function. Then what about my V dot? V dot is as we discussed del V by del x or gradient of V transpose times f of x. So, that is my gradient V transpose del V by del x del V by del x 1 del V by del x 2 as a row vector and then f of x f 1 of x and f 2 of x as a column vector. This is a column vector with a transpose term of that. So, if I do carry out this algebra, I have got a V expression. So, with respect to that I carry out del V by del x 1 and put that and del V by del x 2 and put that and f 1 and f 2 are already available to me from here. Okay, that first one is f 1 and this is f 2 anyway. So, I substitute that and then see that these two expressions cancel out nicely actually. That means, I got a V dot which is equal to 0. Okay, so, obviously, this V dot is less than equal to 0, in other words it is a negative semi definite function. So, we started with a positive definite function and so that V dot is actually a negative definite function and hence it is a stable system. Okay. All that we are telling here is the system is stable, we are not claiming anything more than that. And as long as the system ball oscillates, keeps on oscillating actually, then obviously the system is stable actually. Okay, it is not going to increase its, it is not never that theta and theta dot is never going to go infinity. That is all we are claiming here actually. Okay. All right. What about with friction? Okay, because with friction we know for sure that the pendulum is going to come to 0. Now, can we are we able to show that? So, we have to modify the system dynamics and then tell okay, I have got a KL theta dot term now here. Okay. And then if you carry out the same analysis and all that, you will have an additional term which is coming here as a friction term and all that minus k by mx2. Start with the same analysis, same algebra and you are left out with this expression actually. Okay. That means, V dot of x turns out to be minus k L square x 2 square and that is the difficulty, and in other words this expression is actually we can only claim that it is negative semi definite, it is never negative definite because it does not contain an expression in terms of x 1 and this expression has to contain all variables actually. You cannot leave out one component of on the state space and tell it is negative definite. Why is that? Remember, if I talk about this expression, let us say this expression feels like it is negative all the time, but really not so. Let us understand that part of it, because if I talk about x 1 and x 2, okay, this is x 1 and x 2, all that it guarantees is that this expression will always remain negative actually. Okay, that is fine. But what about x 2 equal to 0? When I put x 2 equal to 0, that means I am moving along this x 1 line, okay, the function is equal to 0. That means, I have got infinite number of points other than equilibrium point for which the function V dot is equal to 0. Okay, but that is not the definition of negative definiteness. Negative definiteness tells that the moment I go away from 0 anywhere in any direction, I should be able to get a negative value, but that is not happening here. The moment I travel in any direction any direction along x 1 axis, okay, my x 2 value is still 0 and my V dot is still 0 actually. So, all that I am able to show is that V dot of x is negative semi definite and that is the frustration really, and if it is negative semi definite, we are still able to tell that system is stable and we are not able to tell system is asymptotically stable, and that is the frustration. We know for sure that the system is asymptotically stable, but we are unable to conclude that using this particular candidate of Lyapunov function, and that is the motivation to why we need to study Lassalle's theorem and all that actually. Using Lassalle's theorem we will be able to show that the system is actually asymptotically stable, and that is what we will study later actually. Okay. Anyway, before moving further, what about this utility for linear time invariant systems, because that is something that we understand well, and then this particular analysis will also give us a tool to exploit it further in many control design application actually. So, let us study this a little bit here, and we are interested in not only any nonlinear system, but we are interested in applying the same thing for this particular linear system x dot is a x, where A is just a constant matrix. Remember, the nonlinear systems by definition are not necessarily linear system. That means, anything that is valid for nonlinear system is also valid for linear system actually. So, I want to verify whether my concepts are right or wrong, number 1, and number 2, it will give me some other tools to analyze and some other tools to exploit in control design later. Alright, so let us start with a Lyapunov function candidate, and x transpose p x, where p is a positive definite matrix, is certainly a positive definite function. We have studied that in matrix theory also. So, if I start with x transpose p x, remember x transpose x means p is identity, and identity is certainly a positive definite matrix basically. But in general, if I put a positive definite matrix here x transpose p x, then v of x is certainly positive definite function. Now, how about kind of analyzing v dot? Now, if you start from here and v dot, remember p is constant matrix. So, v dot is x dot transpose p x plus x transpose p x dot, and x dot you substitute a of x, that means x dot transpose is a transpose x transpose, and x dot is a x. So, you take x transpose to the left and x to the right, you are left out with this expression. That means, v dot is nothing but x dot x transpose whole into a transpose p plus p a into x actually. Okay. So, for stability we aim for something like a negative definite v dot, that means, v dot has something to be like we aim that v dot should be something like this, where q is positive definite, that means, v dot is negative definite if it happens so. That means, if you compare this expression with this one, this is the result that you are getting. So, if you really want a non-trivial solution, that means, this equation is valid for all x which is not equal to 0, then all that we have is, this equation has to be satisfied, and what is called as this equation is famously known as Lyapunov equation actually. So, if you get a p and q solution from here which satisfy this equation, and if I select a p and select a q which will satisfy this Lyapunov equation, I am done actually. Okay. So, obviously, it gives us kind of idea to tell that okay, I got q is equal to negative of that anyway. If I solve for q, okay, this expression gives me something like q is equal to negative of p a plus a transpose p, right. So, if I start with a positive definite p, I can simply evaluate my q, okay, and I see whether this is positive, whether q is negative definite or not, and q is positive definite or not, and then I am done actually. Okay. But it turns out that this is not a very smart way of doing actually, because you can keep on doing that, there is no harm in doing that, but we really want one shot results actually. Okay, that means, we just want to try out once actually that way, and if you really want to do that, it turns out that you have to start with in a little bit reverse direction. That means, you start from q, okay, you do not start from p, you start with q, okay. So, you select q positive definite and then solve for p. Okay. If you solve for p and then show that p is also positive definite, then the result is sure shot actually. That means, either you succeed or you fail, okay, that way, and that is why the procedure is always like that. You start with a positive definite q and solve this Lyapunov equation to get a p solution and see whether the p is positive definite or not actually. Okay, and this is, remember, this is a linear equation. So, the solution does not take computational intensive way and things like that. It is just a unique solution actually what you will get. Alright, there is a theorem which binds up this property and all that actually. Okay. So, this theorem tells us that the eigenvalues of lambda I of a matrix A, okay, which satisfies this real part of lambda I less than 0, if and only if for any given symmetric positive definite matrix Q, there exists a unique positive definite matrix P satisfying the Lyapunov equation. That is exactly what I told now. If you start with the Q positive definite and then solve for P, then this theorem binds up that okay, this if and only if conditions are nice to see, because they are both necessary and sufficient actually. So, just you just try out one time and then you are done actually that way. If you are interested in seeing the proof part of it, you can see this book, page 98-99. And this P and Q are also related by this expression, that is P and Q. If you know Q, you can evaluate P. Okay, but it is seldom done that way actually. We never bother to evaluate P that way. We simply solve this equation to get P. I mean, if you solve this equation, you will get P anyway. So, but this P and Q, whatever solution you are getting, they are also this relationship will be satisfied. Okay. So, that is probably you can see that as verification tool or whatever actually. Okay. Alright, so this is what I have already told. So, choose an arbitrarily symmetric positive definite matrix Q. You can select any positive definite matrix Q by the way. Just solve the Lyapunov equation once and see whether the PA matrix is positive definite or not, that is it. And linear system theories are nice in that sense actually. The results are one shot, your shot and things like that. Just one time you check out and all that. So, if I have a liberty of selecting any positive definite matrix Q, then obviously my natural choice will be identity. Identity is a positive definite matrix. Simplest form of positive definite matrix is identity. Its all diagonal elements are 1 1 1, all are positive, hence it is a positive definite matrix, and algebra becomes simplified for me actually. So, I just select Q equal to identity, then solve for P matrix using Lyapunov equation and verify whether it is positive definite or not. And if P is positive definite, then V dot is guaranteed to be negative definite, and hence the origin is asymptotically stable actually. And as I told before, looking at those eigenvalue properties and all, you can also show invoking Rayleigh inequality and all, you can show that system is exponentially stable actually. Now, this those theorems that we discussed here is all like Lyapunov's direct theorem, and there is a Lyapunov's indirect theorem which we heavily used in engineering problems and all that. So, what it tells us? It tells us I mean that is why this Lyapunov's indirect theorem is the theorem in my view for which the linear system theory is very popular. Otherwise, it will never have been that much popular actually. Okay, what is that theorem? Which tells you that this theorem tells us that let us linearize the system about this equilibrium point, whatever nonlinear system we have, and we get this delta x dot equal to A times delta x. Okay, by linearizing the original nonlinear system about the equilibrium point. And then this theorem says that if all the eigenvalues of this matrix A, okay, lambda I, they satisfy this left hand side property basically, that means real part of all lambda I should be less than 0. That means the linearized system is exponentially stable. Then the nonlinear system, okay, that then for the nonlinear system, the origin is locally exponentially stable as well. Okay. So, all that we are doing is, okay, there is an equilibrium point, we linearize the system and study that linear system. The linear system happens to be stable, it is certainly going to be exponentially stable, and it also tells you that the nonlinear system is also locally exponentially stable. Remember, the linear system is globally exponentially stable. Okay. But using that property, you can always say that the nonlinear system that I started with is also exponentially stable. Okay. So, that is the powerful theorem actually in that sense actually. And that is why these linear systems are heavily studied, and they work and all, I mean they work wonderfully and all that actually. Okay. Anyway, so this is the Lyapunov's indirect theorem, and the easy way to do that also. You just linearize the system and study the eigenvalues of A, and all the eigenvalues are in left hand side. That is what we know for standard linear systems theory. Then not only the linear system is exponentially stable, but the nonlinear system is also locally exponentially stable. The domain of stability can be less, that is another issue actually. So, the linear system domain of stability can be large, but the nonlinear system the domain of stability can be very less. Okay, that is where we need to study nonlinear system, but nevertheless we will be able to claim that, okay, my equilibrium point is at least locally stable basically. Okay. Anyway, so what about instability theorems? See, if let us say we are somehow unable to conclude anything, and like we tried out many Lyapunov functions and things like that, started with let us say x transpose px, did not work out. Then we started with this the kinetic energy plus potential energy, did not work out. Then we tried with something else, also did not work out. Then how many times you will start actually? That means that gives us some sort of a hint that probably we are working in a wrong problem actually. That means maybe the system is unstable, and I am unnecessarily wasting my time in trying to prove that system is stable. Okay. So, what about exploiting the possibility that system can actually be unstable? and that is where you will see a number of instability theorems. Okay, they are not really Lyapunov's theorem, but Lyapunov like theorems actually. Okay. So, we will see some of this, at least one condition which tells us like this actually. So, consider the autonomous dynamical system and assume that this x equal to 0 is an equilibrium point, and V d to r has the following properties. Okay. And V of 0 is 0. Okay. And the second condition, remember this V that we are studying here is not necessarily positive definite, that is why these conditions are necessary. Okay. So, the V d to r should have this property, that means V of 0 is 0, and there exists some x 0 arbitrarily close to x of 0 x equal to 0 such that V of x 0 is positive. That means, if it happens to all such x 0, then only it is positive definite, right. If it is arbitrarily close, whatever happens, but all x 0 like that, V of x 0 happens to be positive, then it is positive definite. But here the condition is much lesser. All that you are telling is there is only one point somewhere which is close to xc for which V of x is positive, that is sufficient to show instability. Okay. Then we are telling that V dot is positive definite, but actually it is not positive definite per se, but V dot is positive for all x in that U set U, where U is defined as follows actually. Okay, that means U is x belongs to D such that norm of x is less than epsilon and V of x is greater than 0. So, all these things I mean kept aside, if in a simplistic language, if you see, if I start with a positive definite function and show that V dot is positive definite also, then obviously system is unstable. Okay. Okay, why does it happen? In other words, positive definite function, as you see that it also happens some sort of energy content behavior. That means, any positive definite function I can associate with some sort of energy of the system, need not be kinetic plus potential, but some sort of energy content there. And if the energy content of the system keeps on increasing, V dot is positive, what does that mean actually? Keeps on increasing, then obviously my system is unstable actually. But what condition tells you, the theorem tells you is, okay, you really do not have to show that V dot is positive definite. All that you have to show is V dot is positive in this set, and this V of x 0 is positive for one x 0. Okay. So, the conditions are very I mean kind of weak conditions, and hence it is easier to show probably. But intuitively speaking, if you I do not have to really worry about so much about that, because if V of x happens to be positive definite and V dot is also positive definite, then certainly it will satisfy these conditions. Okay. So, that is what we are worried about, but V dot positive definite is difficult to show. So, what you want to show is, okay, V dot is greater than 0 in this particular set. Okay. So, x belongs to this domain D such that norm of x is less than equal to epsilon and V of x is positive actually. So, in this particular set, if you show that V dot is positive, it is sufficient to tell that the system is actually unstable actually. Okay. So, under these conditions, it turns out that x of 0 is unstable. Okay. Now, let us review that quickly what we studied in this particular lecture. So, we started with some sort of like motivation, and then tell why these Lyapunov theories are important to exploit, and stability behavior of nonlinear system is not necessarily global, unlike linear systems and all. Then we particularly are interested in x dot is f of x, and if it is x of f of x u and u is also a function of x, that means tested feedback design, then closed loop sense it is still a homogeneous system. So, this is motivation intact, we studied further. X e turns out to be an equilibrium point, but with change of variable and all that, we will be able to tell that x e is 0 and all that actually. I mean with change of variable what we discussed here, then further theorems and all x e is 0. So, if that original system equilibrium point is non-zero, then you have to do this coordinate transformation first and then interpret the system in terms of variable z, then proceed further to show the Lyapunov theorems and all that. Okay. Then we studied some sort of these definitions of open set, connected set, things like that. Then what is called a stable, what do you mean by stable equilibrium, what do you mean by unstable equilibrium, what do you mean by convergent equilibrium, that means the system trajectory ultimately comes back to the origin, in between it can deviate large and things like that, and it happens to be both stable as well as convergent, then we call that as asymptotically stable equilibrium point. Then there is a notion of exponential stability, that means not only it goes to 0 and it remains bounded on the way also, but the rate of decay is kind of exponential decay basically, starting from this difference, that my original distance and any point of time I have a distance from origin, these two distances are kind of related by this inequality condition. And then there are definitions like positive semi-definite, negative semi-definite, definite, all sort of things. This is the definition. We have to select, I mean, some particular v of x, scalar function of course, which satisfies that, I mean, this domain D contains origin, equilibrium point, as well as this condition is satisfied, then it is positive definite, semi-definite, and then hence positive definite, if it is less than, I mean, greater than equal to becomes greater than, then it is positive definite, and if you replace that by less than equal to and strictly less than, then it becomes negative definite thing. Then there are a couple of theorems that we studied. We told, okay, this is like stability theorem first, weakest notion of stability. All that we have to do is we start with a positive definite for Lyapunov function and show that v dot is negative semi-definite. And then there are a couple of candidates that we discussed. V of x, you can start with like x transpose x, or you can start with kinetic energy plus potential energy, and then v dot is something that we compute like this. It is partly selection and partly system dynamics that will come into picture. Okay. And that is v dot is something that we need to analyze here ultimately, and all these conditions that we discussed are all sufficiency conditions actually. Okay. So, if you want to tighten it up the condition and all from stability to asymptotic stability, then v dot has to be negative definite, negative semi-definite is not good enough. And if it is the global behavior you want to study, then v of x has to be radially unbounded. Remember, this is still v of x, that means we can select a v of x which will satisfy that. Okay. And with respect to that selection, v dot of x has to be negative definite. Okay. Then only you can talk about global asymptotically stable behavior actually. Then exponential stability, these two additional condition in addition to asymptotic stability condition. Then we start with this example, kinetic energy plus potential energy for the pendulum, and pendulum what we discussed here is a regular pendulum. That means about this vertical equilibrium point, I mean this swings like that. Okay, this is the thing that we are talking. This is my theta dot all that actually. Okay, so this is the pendulum problem, and we are able to show that the system is stable, but the frustration is even if it is with friction, we are only able to show that it is still stable only. I mean, we are not able to show it is exponentially stable, I mean sorry, it is asymptotically stable, but we know that it is asymptotically stable. So, we need further conditions and then that we will study later. Okay, then this application of LTI system, we started with this kind of this x dot equal to x, which is linear time invariant homogeneous system, and then it tell okay, this has to satisfy a Lyapunov equation. That means, and the procedure is I select a q which is positive definite, then solve this p and then see whether p is positive definite or not actually, and that is a one shot procedure, just one time I have to do, and if it satisfies the system is stable, and hence it is, because it is a linear system, if it is stable it is asymptotically stable and it is globally exponentially stable also. So, that all I can show there. If it does not satisfy, then I am done also. I mean one time if it fails, it fails, I mean that system is unstable actually. Then this theorem is all about that what we discussed, and this relationship is there, but we hardly worry about that. You can think about like some sort of a validation check actually. And then there are indirect theorem, and indirect theorem tells us that if the linearized system is stable about the equilibrium point, then the nonlinear system is also stable globally, I mean also stable in an exponential manner about the same equilibrium point, but the stability domain can be small actually. Then instability theorem, in addition to v being positive definite, v dot has to be positive definite in a rough way, but the conditions are much milder, and these are this is the one condition that is to satisfy. Remember, instability theorems, there are many theorems. You can, if it is this condition you are not able to show, you can show another theorem and all that. You can, so we are not talking here. With that, I will probably stop this lecture. Thank you.